Alright, so hello and welcome. Howdy. Good afternoon. Take a moment here before we get started. So I have another question here on LeetCode. Try to do at least one problem before bed, I think, here. Yeah, so, alright, I guess we'll get right into it. So, the question is, random point in non-overlapping rectangles. You are given an array of non-overlapping axes-aligned rectangles rects, where rect of I is AI, BI, XI, YI. Excuse me. Indicates that AI, BI is the bottom left corner of the ith rectangle and XI, YI is the top right corner point of the ith rectangle. Design an algorithm to pick a random integer point inside the space covered by one of the given rectangles. A point on the perimeter of a rectangle is included in the space covered by the rectangle. Any integer point inside the space covered by one of the given rectangles should be equally likely to be returned. Note that an integer point is a point that has integer coordinates. Implement the solution class. Solution int rect initializes the object with the given rectangles. Rect int pick returns a random integer point uv inside the space covered by one of the given rectangles. Excuse me. Right, interesting. Well, I guess you could just pick a random rectangle and then pick a random point within that rectangle. The problem with that though is that if these rectangles overlap, you have kind of an issue. Yeah. All the rectangles do not overlap. Oh, nice. Okay, perfect. I was gonna say this is gonna be a lot harder if they overlap, but if they don't overlap, it's a little bit easier. Well, every point should have equal probability, right? Excuse me. And it looks like the rectangles themselves are defined by integers. I don't know about this question, man. Got a lot of downvotes. The thing that's tricky is that even if they don't overlap, if you randomly select a rectangle and then select a point within that rectangle, then because the areas of the rectangles are not the same, the selections you make over those areas are not in other words, like the probability of selecting certain points for smaller rectangles is higher than other rectangles if you do it that way. So you actually need to weigh the probability of selecting a rectangle based off of the weight of the area of the rectangle. So yeah, so you just have to factor that in. Don't necessarily know what a distribution like that looks like though. You could do like a random number from 0 to 1 and then say make a piecewise function and say if it's between this value and that value, that's this area. If it's between this value and that value, it's the next area. Basically take the areas of each rectangle, divide them into the total area to give you how much of a section, how much of a probability there is to select a certain rectangle, and then pick a number from 0 to 1, and then depending on which section you're in, that's the rectangle you choose, and then you can just pick a random number within that rectangle. Actually, that's pretty good. That's a good way to do it. How would you do that though? Like algorithmically or programmatically? I think you can do a linear search through you can find the sort of, call it probability value for each rectangle based off the total area of the rectangles, and then you can say You can actually just subtract each probability value until, so if you're between 0, let's say it's 0.2, 0.2, 0.2, 0.2, right, like 5 0.2s. If you subtract 0.2, if you're between 0 and 0.2, and you subtract 0.2, you'll be negative. If you're between, if you're larger than that, it won't be negative. If you subtract another 0.2, if you're between 0.2 and 0.4, then it'll be negative, or less than or equal to 0. You can do it that way. I think you just keep subtracting until you're less than or equal to 0. Excuse me, and that'll tell you which one that you're at. Or you can assign to each rectangle a range, sort of a half open interval, and then you could loop through each rectangle and say, or is this probability within the range for that rectangle? I think that's the way to do it. So we'll do it that way. Yeah, I think that's the way to do it. So, okay, fair enough. And we kind of construct all of this when we, how many rectangles are there though? Before we dive right in here. Only 100 rectangles. I guess the size is relatively small. All the rectangles do not overlap. At most, 10 to the 4th calls will be made to pick. Okay, that's fine. 10 to the 4th times 100 is no big deal. Okay, we should be okay. We should be fine. We're going to use it in random integer library. See if I can remember how to use this properly. Vector of vectors. Here we go. So I think I have the idea. I think I got it. I think I got it. Okay, so we have standard random device RD, which will give us one random integer that we're going to use as a seed. We're going to have a 19937 missing a twister generator, and we'll seed that generator. Actually, this is the constructor. Sorry, this is I did this wrong, or almost did it wrong. Actually, these have you can have, what do they call that? You can have static constructors, not static constructors. What do they call that? You can have a constructor for you can have a default value basically for this. So we actually don't need to put these in the constructor. It's kind of learning that about initialization and things. It's kind of reading more about the C++ language. So then we have random distribution, which is, we want, int distribution. So we can do, it's actually going to be uniform. Int events. There's uniform real distribution, uniform, I have to check it, take a look, see what it says. I know there's real int distribution, but there's also the uniform, it is uniform int, uniform int, okay, what it was. And we're going to just call that distrib, or just D. And we're going to use no parameters. So we'll set the parameters when we want to use it. And then we're going to say rects. We're going to have a list of vectors. And these are going to be doubles. We're going to use for precision. By the way, applications that use real numbers tend to use floats rather than doubles. There's sort of rationale for that, but we're going to use actually, we're going to use a tuple of doubles. So yeah. And we're going to just call these sort of rect probabilities. So we're going to process these rects. So we can say determine total rect area. So I'll have int area is going to be standard accumulate it's a fold expression, I guess, or something. I'm not sure exactly. Let me see. What does it say? First, last, and an op. Yeah, we want an operator, binary operator. Yeah, that's what we're looking for. Yeah, we want an operator. So rects begin, rects end, and I think the binary operator comes after the initial value. Yes, it does. The initialization value. Start with 0, and we'll have a auto add area, we'll call it. We'll use our own function to compute the area and add it. So we're actually going to have two values. We're going to have int sort of current, and we're going to have standard vector of ints, and this is going to be a rect, and it's going to be a const, so we don't need to modify it. Rect, and we're going to say return. We're going to say int area, rect area is going to be just XYZ, we'll say, or we're just going to add those things. We're going to compute that into current plus rect area. And the rect area is very straightforward. It's delta y times delta x, which is A is x in the bottom left, which means that A is less than x, which is the top right. So delta y times delta x is, so we'll say, we're going to do it this way. So int A is going to be a rect of, we said, 0, B is rect of 1, C is rect of 2, not C, X is rect of 2, and Y is rect 3, right? And we kind of assume those things based off of the, format and the sort of how things are specified here. So X is larger, it's because of the top right, it's larger than A, and because Y is in the top right, it's above the other B coordinate. And also we're assuming that Y, we're assuming sort of a 2D Cartesian plane where up is increasing Y and to the right is increasing X. And obviously that's not always true for certain like world maps, I guess, or however you want to express it for software, that actually the Y increases as you go down and the X increases as you go to the right. Certain sort of, I guess, software formats, I suppose, for certain software formats for, I guess, programs. How programs sort of define their two-dimensional planes tends to be, sometimes it's that way rather than the way we would like to understand it here, or yeah, the way that we understand it here. So that's the total area. Now, excuse me. So actually, compute area is really what we want, because we're going to reuse this function. Okay, compute area with a rect, and we're going to just return this altogether. And then this is going to be there we go. That's a little bit easier. So, or not easier, but we want to reuse this function, this compute area function. And we're going to say double, or we're going to say compute and save the probability range each rect. So we're going to say for const auto r and rects, do it this way. We're going to say int rect area. It's going to be compute area of r. We're going to say double rect probability. It's going to be this rect area times 1.0 divided by the total area, right? And then now the issue is we want to actually store in our rect probabilities. I guess the question is, we pretty much want like a mapping of, we also kind of want to store these rects as well. Yeah, so we don't want to modify them at all though. Just copy them. So now we say compute and save the probability range for each rect. So compute this directly, I think, here, and we want rect probabilities to use dot pushback standard make tuple. Now the thing I'm wondering is, like, if I don't know, organize this. I guess we could do it this way. I think this is fine. You know, we'll do the other way around. We'll do it when you subtract and you get less than or equal to. I think it's simpler to do it that way. You subtract and you get less than or equal to 0. I think that's a better way to do it. Yeah. So okay. I think it's just simpler. It's a simpler idea and simpler approach. It's generally simpler. So okay. Rect probability. Okay. So rect probabilities, compute and save the probability range for each rect. Copy rect array for use later. Yeah, so pick. We're going to have our distribution. So we say determine which rect to select based off of the pre-computed probabilities. Okay, and that will be, oh, you know what we need to do actually? Also need a uniform real distribution as well. Double. So di and dr, and I think both of those have default constructors. I think, could be wrong. We can add them though if they don't. So dr, we're going to say dr.params. It's going to be, I think we can do it this way. Actually, we might not be able to. We probably need to do it this way. So we can do standard uniform real distribution of double param type is going to be equal to, let's say p, or p's, I don't know, just p. And we're going to use two values. It's going to be 0.0 to 1.0. And actually, oops, these you also need to use a next after, which is interesting. So we'll do double, we'll just call it, I don't know, temp is equal to standard next after, because we want this to be inclusive with 1. 1.0 and standard numeric, which we need limits here. Standard numeric limits of double, and we're going to say max. We're going to go towards the maximum, right? Standard next after, and we're going to use temp. Okay. All right, here we go. And then we set params to p. A little bit complicated, but yeah, that's what we use. And then we say dr of gen and we say double, we'll say random int, random probability, or random p, rand p, dr gen, and then we say for int I equals 0, I is less than rect.size plus I. We're going to say so we'll say rand p minus equals rect's probability of I, this one, of I, if rand p is less than or equal to 0, then we're going to break and we're going to set int which equals, we'll start off at 0, and we'll say which equals I, right? We'll do it this way. And then now that a rectangle has been chosen, uniformly select a random point from that rectangle. Oh no, is this even harder than I thought? Because this is random integers, not random points. Random integer points. So actually, the probabilities are slightly different for each of these, by the way. It actually depends on how many points there are in the rectangle, not the area of the rectangle. Well, they're all integers to begin with, so actually I think the number of integers is still correct, so I think we're actually okay, but how many integer points you have between like 0, 0, 2, 2, I think it's actually a few more points, believe it or not. Between 0, 0 and 2, 2, you'd actually get 9 points. So 0, 0 and 1, 1, you have 4 points, the 4 corners. Interesting. So yeah, basically you just have to add 1 to this area, which is kind of interesting. It's not the total area, it's the total points that can be selected from a given rectangle. Compute points. points. It's not area, compute points. And that's going to be, believe it or not, +1, +1. And then add points. We're going to say compute points. And so now it's not add area anymore, it's add points. It's not area, it's total points. Interesting. We'll say rect points, compute points. The rect probability of selection is then the rect points times that divided by the total points. A little bit confusing, slightly different, but I don't think we would get the correct probabilities if we did it the other way around, the correct distribution. So now we have a rect probabilities. Right. Okay. Same kind of idea, just slight adjustment to get the sort of correct algorithm. Now the rectangle has been chosen. Uniformly select a random point from the rectangle. Right. So now we can do our distribution here. Our int distribution. So uniform int distribution. Int param type. Now this is going to be from our rect. We're going to say int a equals rects of which b rects of which of got it. Of 0, 1, x is 0, 1, a, b, and then x, y is the next one, yeah. 3. Okay. Okay, and we're gonna pick a point between, this is gonna be the x coordinate and the y coordinate, right? So the x coordinate is gonna be between a and x inclusive, and then we're gonna do the same thing for b and y inclusive, right? So a is smaller than x because of the bottom left, b is smaller than y also because of the bottom left, right? And the top right is where x and y are. Okay, got it. So now we can do int x coordinate, let's call it, is going to be, we're going to say d of r per dot params, so di dot params. We're going to set that to p. And here we can actually just say p equals, I think. It actually, well, yeah, we'll do it that way. Try this, I guess. That may or may not work properly. Okay. Yeah, so then this is going to be d of I of gen, and then int y coordinate is going to be a similar thing, although we have to set the parameters. So di dot params, it's p again, and that's going to be di of gen. So generate x and y, the x coordinates, y coordinates, and then we say return x coordinate, y coordinate. And that's just a vector of these two values. And let's see if this compiles. Let's start with that. RD. Unknown type name RD. Okay, so these don't necessarily have knowledge of each other. It's right here though. I guess when you initialize it, you can't do it this way. That's okay. It's not really a big deal. You could just say or just seed random number generator. So gen is standard Masonite twister 19937 with RD as the seed. The seed will give you like a try to give you like a random value that's sort of like from the hardware, I guess. Alright, so dr params p, did you mean param? Is that what you do? Param, not params? I don't actually know. I don't remember really. I've seen it before, but I don't recall if it's params or param. It's a little confusing how this is done. It's param, params type. So it's interesting that. Oh yeah, okay. Say PI, we can say. As in params, integers, I guess. No way to overload this. Okay. Yeah. Because this is a constructor. Can we do? I want to set these values. Can you do that? Does that work? No. It's kind of annoying. There's no easy way to do this. I mean, I could just create a new object. Just call this PI1, P1, P2 or something. Just keep it simple. Really doesn't need to be that complicated. AX, BY, P1, P2. Alright, let's give that a shot. See how that goes. Hey, it worked. Okay. Sweet. Alright, now, is this correct? That's the question. I think so, but we'll find out shortly. I just wanted to see if there is a way to like easily modify with the, like, so I have to create a whole new variable for this. Let's see. So somewhere in here is this, no, not the operator, reset, what does that do? Param, min, max, gets or sets, okay. So I get that. Oh, okay. Not really what we want. Reset's probably not right. Const param type params. Yeah, I mean, you basically have to create a new params object. What's interesting is this object is of param type. It's literally just param type. It's not clear what this object is, though. I think this is just a struct. But that's the thing. It's like, it's not really obvious what this is at all. What is this param type? How do you find that? I don't know. It's not there. It's nothing. This is like one of the few spots on C++ reference, I guess, where you just kind of get stuck. Where you're like, what is this parameter object? Template parameters. Number types. The type of the parameter set, see random number distribution. Yeah, see, that's weird. the type named by D param type, which, excuse me, satisfies these things. Constructor taking identical arguments, each of the constructors of D that takes parameters corresponding to distribution parameters, has a member function with identical name, type, and semantics as every member function of D. Returns a parameter of that of the distribution, member type def, distribution type equals D. Gulp. D has a value of type D. X and Y possibly cons values type D. P possibly cons value type P. G, G0, G1, G2, all values with type satisfying this. Specializations. Following expressions must be valid and have their specified events effects. Compile time. Okay. That's interesting. So these are done at compile time, these things. Is that right? I don't know. I'm so confused. I don't know. Oh, expressions. Okay, gotcha. Never mind. They're just expressions. Turns P. Excuse me. D.param P. Post condition D.param is equal to P. But how do you modify P? Do you just have to create a new one every time? Same as P's construction. Parameters of the distribution may be changed either permanently by using param P, just the duration of a single operator call by using D of GP. Ah! Haha! That's what we're trying to do. Okay, that's what we're missing. Const member function. Repeated D of G. Haha! So, well, that's not necessarily helpful though, because you still have to construct P to use it. That's kind of what I'm trying to do. I'm trying to avoid using constructing P. Yes, const param type params. Okay, well, whatever, it's fine. Not really a big deal. So it looks like you do have to construct this every time in order to use it. Construct one of these each time. Anyway, I just trying to be a little bit more clever about how I do this, I guess. Where's pick? So pick is 10 to the 4th calls made to pick. So 10 to the 4th picks. Alright, so we want this here, and we want 10 to the 4th calls. Let's take a quick look here and say 10 to the 4th calls to pick. Alright, so echo quick awk script if we can to print this. So we do for I equals 0, I is less than 10 to the 4th, 1, 2, 3, 4, plus I. Pick S is going to be equal to S pick. I think this works. We do it this way. We actually want a comma here. These should be escaped because we want a comma here. Alright, so we'll do pick with a comma. So for spick, and then at the end we just print. I don't know what this is going to do. Oh, there we go. Wow. Look at that. Okay. Okay. So we want solution, pick, yeah, all right, that's fine. We can just put this into a temp, and then temp, go to the front, say we want solution, okay, 10,000 picks. Oh, we need 10,000 of the other thing too. Oh boy, we'll get to that in a moment. Okay, sure. Right, let's. Oh, okay. You do notepad.exe temp. Aha. Check that out. And now copy paste that. Put that all in there. And we need 10,000 of these guys too. Okay. So, alright, get those two. Close notepad. Hopefully. Oh, yeah, okay. Thought I may have had something incriminating there. Same deal. We have an aux script. We have print s. I have a for loop. Int, or just not int I. Less than 10. 1, 2, 3. 1, 2, 3. Plus I. S equals S. And we're going to do these guys now. Okay. Also temp, notepad, temp, and copy that. Yeah, there we go. Okay. All right, there we go. We got our massive test case, which we must test in order for this to work properly. We can also close this. Whoa. Interesting. Okay. Hey, it's correct. Can we add a few more rectangles to our enormous test case? Scroll all the way down to get to what we just posted. Okay, here we go. Right, we have to go even further down. Okay, a little, no, not quite. Okay. So we want a few more rectangles. Let's do like 5. It should be like 100, but they don't overlap. So we got 1, 2, 3, 4, 5. Okay, so -2, 1, 1, 2, 2, 4, 6. Let's do like 100, 100, and 101, and 101. Let's do like 50 and 50 and 52 and 52, and then I don't know, 25 and 30, something like that. I don't know, some random thing, something that's clearly not overlapping, but also simple enough for me to just kind of compute it right there, or to type it. Let's see how we do. Okay, maybe, I don't know. Let's try it. Hey, got there. So there we go. Just some practice. Just maybe a more efficient way to do this, but I like this. I think this is okay. So yeah, I think it should be relatively clear what I did to make sure the distribution is correct. Calculated for each rectangle how many points are contained in that rectangle. Added all the points for all the rectangles together, and then for each rectangle you can divide the number of points for that specific rectangle by the total number of points to get the probability that you would select one of those points from that rectangle. And then I gathered all those probabilities up, and I said, okay, we're gonna have a sort of step-by-step function, I guess, where it's really like a piecewise function where we're going to try to find which rectangle, given a probability from 0 to 1, which rectangle does that probability correspond to. So randomly generate that probability, and then we're going to just keep subtracting from the rectangles the amount of probability there is in the same order each time, by the way, so that once you're less than or equal to 0, that's the sort of section that of probability is represented by that particular rectangle, and that has a certain index, and so we go back now with that index to grab the rectangle coordinates, and then so it's kind of like a linear search through our rectangles to find which one corresponds to that particular probability, and then and I think you can do that in logarithmic time potentially. I don't know if you can do it in constant time. You need a kind of some kind of a hash map, but you need to hash a range of values to this. So not entirely sure how you might do this using logarithm, or binary search. I think the binary search you can do is you can just say like you can have it's not a cumulative probability, but it's like you add the probabilities, and those become sort of the points where if you have a probability between two values, then that represents I guess it would be the index on the left, we'll put it that way, right? So then you could do actually logarithmic search. You could optimize this slightly to do binary search through the sort of assorted list left to right. Actually, I kind of want to implement that, show you what that might look like. Yeah, let's do that. So yeah, we'll have rect probabilities, cumulative rect probabilities probably. Yeah, cumulative. Let's do that. Actually, let's show what this looks like. It's another way to do this, slightly more efficient. And we're just going to say double previous equals 0. So if cumulative, previous plus rect probability. Yeah, do it that way. Okay. So there. Okay. Time for bed. So the previous will be 0, and we're going to add 0 to the rect probability. So yeah, okay. I think this is right. So you do it this way, and then what you do instead of when you search is you do not perform this search anymore. Now you do an upper bound search. So this is going to be, instead of this, you're going to say standard upper bound of, what is this? This is cumulative. Well, we can do auto just P's reference. Just do it this way because it's just a gigantic. It's just an absolute enormous like alias or absolutely enormous name, so we'll just make the name shorter. And we're going to say, so this is an upper bound. The value we're looking for is the first value that's greater than or equal to the probability. There's an upper bound and a lower bound. Lower bound is greater than, and the upper bound is greater than or equal to. Excuse me. I think that's how it works, right? To like 1, 2, 3, 4, 5. Lower bound for 3 would give you the first value that's greater than or equal to, which is 3, and then upper bound would give you the greater. So we're looking for the first value that's greater than, I think. Well, greater than or equal to, yeah. Well, if it's equal, that's actually, yeah. So we want greater than or equal to. So we actually want upper bound, yeah. Greater than. First value is greater than. And we actually want 0 to be in this initially, believe it or not. I think so. If you had 2, 2, 2, 4, 5 times, you would have 2 for the first value, 4, 6, 8, 1. And the first thing that's larger than 1 goes off the edge, right? So you subtract 1. Excuse me. To get the last index. And the first thing that's larger than 0 is the first value. However, everything less than or equal to 0.2 should be the first. So we could subtract 1 there, but that'll actually go to the -1 index, not 0 index. If we go to, so actually, it's kind of interesting. It actually should be greater than or equal to. Yeah, it'll be greater than or equal to, and it'll be exactly, and it'll be exactly that index there. Which is kind of interesting, yes. So we don't need to do what I was just describing. So lower bound is what we want. And then we're going to say which is going to be then pointer minus PS begin. And I guess it would be sort of the distance between these two. This actually is fine. I mean, this should calculate okay. So what do we get if we do this? This is compile. Let's start with that. Always start with that. Always. No compile. No compadre. Excuse me. Lower bound. We have algorithm, right? Whoa! We have a storm. I hope that'll be okay. Uh-oh. There's an aggressive storm. Uh-oh. I think I'll be fine. I hope I'll be fine. I don't know. I don't actually know what's going to happen here. Oh boy. Oh, we don't have the value that we're comparing it to. I totally forgot. The lower bound that we're looking for is we're using as a value is this rand p. That's my mistake. I forgot about that. Totally forgot. Hey, oh, it's still correct. We're still correct. Okay, I think. I hope. I don't know. Let's see if we can submit this. If it'll function. Hey, okay. Not much more efficient though. It's a logarithmic search at least. A little bit less memory. So yeah, this is a more efficient way to do this, by the way. This is logarithmic instead of linear in n log of n, where n is the number of the rects. It's not much better if you only have 100 rects to look at, but if you had like 1,000 or 10,000, then it would start to matter a lot. Because if you have, let's see, 100 log, let's see, log 100 is 2, or it's more like log base 2. So log of 100 divided by log of 2 is like 7 compared to 100. I mean, that's considerable. I want to say something like there's some overhead involved with actually performing the logarithm and something like that. I don't know. It's not necessarily the most obvious thing. Obvious thing as to why this isn't necessarily very much faster when you only have like 100 rectangles to look at. I guess because most of the test cases don't actually have 100 rectangles. That's probably why. That might be the reason. They would have to have like a lot more test cases with a lot more rectangles to really really see the difference. But yeah, it's a slightly more optimal way of doing this. But yeah, I don't know what they did to make this even faster. By the way, I think 72 was something like 70 or 80%. Something like, I don't know what it was exactly. Let's see if we submit again what we get. But I'm gonna go. Thank you all for watching. 87% was 60. It's just like a kind of random. I'm gonna go. Thank you for watching. Appreciate it. I don't know if I'm doing another number. I think I'm gonna just go to bed. Got church in the morning, and then got church, and then attending a sermon tomorrow, and then we're meeting with the congregation. That's the way I express it. Attending a sermon and meeting with the congregation tomorrow. I think after that, I'll look to. After that, I will look to. What do I want to do? What am I going to do? Sorry, just give me a second here. I think tomorrow, if I'm lucky to make it to tomorrow, by the way, no days promised. I'm going to look to study some more problems. I think I'll try to do that. Try to come back sort of after the sermon and solve more problems. And do it that way. So yeah, have a nice day. Take care. Talk to you soon. Or have a good rest of your night. Take care. Talk to you soon.